Okay. Hey, good afternoon, everybody. My name is Alexander Poth, and today I'd like to talk about the automation of firmware analysis for IoT Linux devices. And the reason is firmware analysis contains a lot of basic simple steps, or mostly a lot of basic simple steps. And we can try to automate that, right? I wrote 2 simple Python scripts, which I'll show you later, which can automate this process. But at first, who am I? I'm a junior pen tester at Eurofin Cybersecurity. I have a degree in industrial engineering, which is very uncommon because I think most people in the InfoSec have studied something like computer science, but I was always interested in capture the flags, for example, or computer science in general, so I decided to get a job in InfoSec. And yeah, I wrote my thesis about Linux firmware security, which is also a part in my talk here. So a firmware analysis can be very, very complex, right? But you have always some basic, simple steps which you can do. For example, check if the firmware is encrypted, try to get the file system out of our binary, and search for interesting files inside our binary. And I did everything for Linux firmware, because many IoT devices are running on Linux. And yes. So we can divide the whole process of firmware analysis into 2 steps. First one is the static analysis. The second one, the dynamic analysis. And in the static analysis, we have no execution of the firmware, right? We just look inside our image and try to search for any interesting files, like any encryption algorithms, weak encryption algorithms, stored credentials, something like that. And in the dynamic analysis, we are analyzing during operating time. So we're trying to execute our firmware and look how is our firmware responding. Okay. So at first, I like to talk a little bit about the static analysis. What we are trying to do here, at first, we like to check if is our firmware encrypted or is it not? Because if the firmware is encrypted, it will be very hard to get any information out of it, right? So of course we can check, are the encryption algorithms weak implemented or something like that, but mostly we can't get any useful information out of it. Okay. But if the firmware is not encrypted, we can try to reverse the whole file system out of the binary. And in our case, so that's our Linux file system. And if we did that, we can search for any interesting files, for any vulnerabilities. So. So I like to start with the check for encryption. What we can say is when a binary is encrypted, the entropy of the data is high. And in our case, we just say entropy equals to the randomness of data, which is not for 100% right. But in our case, we just say that. And to demonstrate that, I created 2 different strings. The left one is AAA, BBB, CCC, and this string is ordered in some way. Why? Right. So we can say this string has a low entropy. And on the right, we have a string like CBA, BCA, BAC. This string looks like chaos. Okay. So we can say in this example, we have a high entropy. I also created 2 JPEG files. On the left, you can see an original JPEG. And in the original JPEG, the entropy is falling and rising over the whole data. And on the right, I encrypted the same JPEG, and as you can see, the entropy is continuously at the maximum, which is 1. So to check if a binary is encrypted, we can check the entropy with some well-known tools. So I picked up 2 tools which can easily be used for an entropy analysis, very easy. The first one is Ent, which is a command line tool. I used that for my little scripts, which I show you later. So it comes with a few options and is very easy to use. And on the other side, what I can recommend is binwiz.io, which is a web service. You can just upload your firmware image, and binwiz.io creates you a great visualization of your firmware. Here on the right, you have an unencrypted image, for example, and on the left, this one is encrypted. So after we checked our binary for encryption and we found out it's not encrypted, we can try to reverse any files out of our binary, okay? So, and just for definition, the reverse engineering is the reversal of the development or production process from the product to the design or the source code, but in our case, we just try to reverse Linux directories and Linux files out of our firmware image. And like you can see here, we have a firmware binary, and we try to get out our Linux directories, such as etc, var, proc, opt, etc. And maybe we can find any interesting files inside there. For example, any credential files, PHP, web files in general, or config files. And of course, you can do this process manually by yourself. You can just look inside the binary and extract everything manually, or you can use tools for that. And one really cool tool is Binwalk. Binwalk is a tool which is able to search for known signatures inside a file. And to demonstrate that, I downloaded some random pictures. Here, for example, a cat picture, a PNG. I also created a zip file with some random content in it. And what I did was I just wrote everything inside a self-made custom file. I just did that with cat and and if you now do an XXD and a hex dump on that, you can see the whole hex data of our self-made file, right? And what Binwalk does is it goes through the hex code and searches for any well-known signatures. For example, JPEG has its own signature, FFD8, FFDB. PNG has its own header, its own signature, and so does zip. Okay. So Binwalk is not just able to search for these signatures, it is also able to extract any data out of it. So what I did here, I did a binwalk on that file, which we created with the extraction parameters. And as you can see, Binwalk was able to find our JPEG signature, our PNG, and our zip file. And it could easily extract everything out of our image. We have our cat image, our zip file, our PNG, and it was able to extract the content of the zip file as well. So in this example, I did a binwalk on a real router firmware. I think it was a TP-Link router firmware. And as you can see, Binwalk was able to find our U-bootloader. It was able to find our U image, which is our Linux kernel, and it found some LZMA compressed data, which is our Linux file system. Okay. And it was also able to reverse our file system, our Linux file system, out of the image. And of course, to analyze the U bootloader, the kernel image, is also very important. But in my talk and in my tool, I'm just focusing on the root file system. So we checked our binary for encryption. We found out it's not encrypted. We were able to get any data out of it, our root file system, and now we can search for any interesting files. So one step of this analysis could be to search for stored keys inside the file system. Very often developers are storing, for example, private keys inside the image. And if we can extract these keys we can authenticate to their services, right? To any cloud services or web servers, whatever. So it is also always very important to look for these files. You can, for example, search for any known file names like host keys, authorized keys, IDRSA, and so on. But sometimes you don't have any file name and you have to do it with another way, but I will explain it later. So similar to this search for stored keys, the search for installed web servers is also very important. A lot of IoT devices have web servers running inside their binary. For example, so that a user can log in, do some configurations, watch camera stream, etc. And if we can extract these web servers, we can look what version is it, right? And if we know the version, we can look online, okay, are there any known vulnerabilities or maybe even exploits there? So it is also always very important to look for these web servers. And what is even more important is what is running on the web server, right? So we should always check, are there any web files inside our binary? Because custom-made web applications are often a famous target for attackers, because developers have often no clue about how to implement a real secure web application. So we should always search for any web files like PHP, ASP, CGI, and have a closer look inside these files. Maybe we can find any, for example, command injections inside the source code. We can do this process manually, or we can just use any well-known tools. For example, SonarCube, RipSwap. These are very well-known, very good tools to scan our source code automatically. Similar to the search for web servers, we should also search for any other binaries. For example, what you see very often is BusyBox, the BusyBox binary. And these binaries are very often outdated or maybe even self-made. And if we found some outdated binaries, we can always check, like the web servers, we can check for any vulnerabilities or exploits. And if the binaries are self-made, we can always try to reverse them, right? And whatever, Radar, Ghidra, IDA, and so on. So what could also be very important is to look for any configuration files in the binary. Why is that? Because insecure configurations are one of the most seen vulnerabilities. And this could be misconfiguration that permits directory listings. I think some of you guys have already seen that, where you can try to access any web page and suddenly you have a complete directory listing. This is a very common misconfiguration. And what is also very often seen is the use of default credentials like admin. So you should always check your configuration files inside your binary. So, for example, you can search for .conf, .cfg, cfg, .etc, etc. So I talked about searching for config files, web files, keys, etc., but very often a developer is also using self-made files, right? And we don't know the name of the files, so what we can try to do is we just look in every file in our binary and search for any strings, for example, admin, root, password, private key, secret, and so on. And maybe sometimes we find hardcore credentials or, for example, poorly implemented token creator or whatever. And this should always be done. Okay, I have shown you some basic steps for which kind of files and strings we can look for. And now I will show a small safe-made tool which can automate this simple process. You can't see anything. Okay, here we are. It's very small, isn't it? Okay. So the tool is asking me for any image file. So I already prepared some images here inside that folder, and we have some, here image which is called dsl.bin. I just take that image, just type here dsl.bin, and now the whole process is starting. It just does the entropy analysis. It creates some output. I will show you that later. Now it's reversing the whole binary. And it said, whoa, I found an etc on bin directory, a var directory. And this is probably a Linux file system then, right? And here it searches for any interesting files. It looks for Linux credentials, SSL files, config files, databases, and so on. And in this section, it looks in every file and searches for any interesting strings. I think it finished. Okay, it wrote any output inside my output folder here. Here's the folder dsl.bin, which was our image. And here we have some outputs for our entropy analysis. It's very small. So it creates some output for our entropy analysis. But what is even more interesting is our reversed file system. So it was able to reverse our whole Linux file system out of here. And here it shows what interesting files could be found. So it creates a HTML file with some hyperlinks. Here, for example, it found some config files, other binaries. You can access them through right here. And here, for example, it found password string in some files. We can just click here, what it found. Okay, it found some standard credentials here. So this tool is no rocket science, right? But it can save a lot of time. So what I have shown you were some basic steps to search for interesting files in the binary itself, and which was a part of the static analysis. Now I will talk a little bit about the dynamic analysis. And we can do the dynamic analysis in two ways. We can run our firmware on a device, but very often we have no device, so we have to emulate the firmware, right? To emulate the architecture where our firmware is running. That is right. And there are some cool tools out there to emulate the images. The most known emulator for any architecture out there is probably QEMU. QEMU is very mighty, very powerful. It knows almost every known architecture. It comes with many pre-made configs for different chips, etc. But in my opinion, it's very complex, and if you had never done anything with QEMU, can take a lot of time until emulation is running. So, but what the cool thing is, on top of QEMU, there's the Firmware-Analysis toolkit, and what it does, it looks inside the binary itself and searches for any information about the architecture, CPU, chipset, etc., and loads the fitting QEMU configurations. So it does all the complex parts for you. So it's very easy to use, but sadly it was not working with every binary. I think 80-90%, just very sad. But because it's very easy, I decided to use this tool for my little scripts. And this is how we do use fat to emulate our image. So we just execute fat and type in the path to our firmware image. It will emulate a network interface, I marked it here, and it will give us an IP address. And if we now execute our firmware, we can just access our running firmware via browser or run our well-known pen testing tools, right? And if our firmware is running, we can, as I mentioned before, we can run our standard pen testing tools. We can run an Nmap on that, port scan, GearBuster, directory fuzzing, web app scanner, Burp, which is also very popular for web applications. But these tools, mostly except for Burp, can very easily be automated. And I will show you that. Oh, come on. Oh, good. So I just prepared the FAT because it takes a little bit time to set every configurations, etc. So I just typed here the path to a firmware image, which is an ASUS router firmware image, and it was able to emulate, to create a network interface with an IP address. Now I'm just executing the firmware, and I think this will take about 20-30 seconds. Great. So our firmware is running and we can access it. So now I can show you my little tool, what I created. Some technical problems here. Okay. Okay, I called this one Lazy Lily. And I executed it, and it asked me for a project name. This is our directory where our output files are written in. Okay, so I just type, for example, B-sides. And now it's asking me for the module we want to use. And I just prepared some modules here. I will show you that. Here in the B-sides folder. Okay, we have 5 submodules inside here. I think you can see that, right? So every name has a small number in front of it, and this is our order, okay? So it will, here in this directory name, we have the name, the number 20, after that 25, 30, 50, 60. So it will run every module in this order, and if we change the order, we can just change the number, okay? So I'm just loading the B-sides module. And now it's asking me if everything is right. It just shows the order again. At first it will do a gearbuster, a NICTO, an nmap scan, and it will then join all files together. And now it's running. So it runs through the whole modules, and yes. What is really cool, you can put in any IP address inside that file. So imagine you are a pen tester, a customer comes and says, hey, I have 10 servers or 10 IP addresses. You just type in every IP address there and let it run overnight. So you can save a lot of time for the basic steps, for the port scanner, directory fuzzer, and so on. Yeah. Okay, that's finally it. Is it possible that I'm doing a selfie with you guys, because this was my first talk? And any problems? Can raise your hands? Oh? Great. So thank you very much. Are there any questions?
Yeah, maybe. How do you start at the beginning? How do you extract the firmware to get the bin file?
Do you mean in the program itself, or
no? Just like when you have the hardware in front of you, like how would you extract the firmware?
Well, sometimes you get the firmware, right? You can, for example, download the firmware if you have a router or IP camera from TP-Link, ASUS, or etc. You can just download it.
Okay.
If you want to get the firmware, you have to dump it.
Yeah.
But that's
okay.
Sorry?
Can you please repeat the questions?
Okay. So mostly or sometimes you can just download the firmware. For example, if you have you are a developer of any device, you can just put your firmware online so everyone can download it. So I just did not dump any firmware or something like that. So I did all tests on existing firmware images, which everyone can download.
Or if you have certain hardware and it has got a mobile application, and at times the firmwares get updated over the air. So what you can do is you can listen the update and you can get the entire firmware from your mobile application itself. Or you can check out the EPROM. Mostly with the EPROM, if you read it, you will definitely get the firmware.
Yes, that's right.
Do you have any tools for partially encrypted, firmware images, in which some part is plain text, some part is encrypted?
you want to encrypt some parts, or
let's say that you downloaded something like a blob, and a part of it is encrypted and a part of it is not encrypted.
No, I've no clue about that. And you probably have a really hard time.
You had that entropy diagram.
Yes.
And it showed high entropy almost everywhere with a ditch.
Yeah.
And you could extract the file system afterwards. Wasn't it
it is very difficult to... sometimes you have compressed data, and sometimes you have encrypted data. So it's very hard to automate the difference. So that the program says, okay, this is encrypted and this is compressed. So if you got a compressed image, the entropy is also very high. Yeah.
So in this case, it was compressed.
It was compressed.
Okay.
Yeah.
The tool you had to generate a QEMU config from a firmware seemed pretty cool.
Yeah.
How automated is that? You mentioned it does take some manual work.
You mean the Firmware-Analysis toolkit?
Yeah, to get to a QEMU configuration from Firmware.
Yeah. It's very easy. You just download it, do some pre-configurations. Takes about 10 minutes.
Do some pre-configurations?
Yeah, 10 minutes. You just have to pre-install some tools.
Okay, but as far as actually determining configuration, it's pretty automatic.
Yeah. But as I mentioned before, it's not very stable. So I would say in my cases, I was able to run maybe 80% of the firmwares. So if you want to really get sure to emulate the image, you should probably do that with QEMU. But as I mentioned before, this is very complex. You need some time to do that. But with QEMU, you can almost emulate any architecture. Any more questions?
Thank you very much.
Thank you.